Okay, so this is a little bit weird that, I mean, conducting a class with no students, but it is what it is. And we as faculty, we have to do justice to the course. And hence, you know, I will be carrying on with recording the class and providing you with the material which will help you prepare for your exam, the final end semester exam. And in case if you have any doubts on this, you can always feel free to get back to me. Okay, so in the last class, we started discussing hydraulic servo systems, and then we kind of got stuck at one point saying we got stuck here specifically that how come Q1 is becoming equal to Q3 and Q2 equal to Q4. So okay, this is what is the explanation. So if you look at it, the volume of the liquid in the overall system, which is what I'm marking here, so that remains constant, right? Because we have, if you look at it from if you look at it from the fact that nothing is kind of changing in terms of, even though we are moving this piston, right, the volume is not changing, the volume remains constant, right? So what that means is the amount of liquid or fluid flowing into the system, and what are the channels through which the liquid is flowing into the system? It is one, right? I mean through port 1 and through port 2, right? And what are the ports through which the liquid is exiting? Port 3 and port 4, right? So the fact that the volume remains constant, that means that whatever liquid or fluid is entering the system must be exiting the system also, right? So that means if we look at the symmetry of the structure, the fact that we have moved the piston X from the left hand side to the right hand side, if we see the aperture or the port area created on port 1, and if you look at the port area created on port 3, right? So these two ports, they are symmetrical, right? So it is fair to say that since the volume of the liquid is remaining constant, right? Since the volume of the liquid is remaining constant, the amount of fluid entering port 1, right? The same amount of fluid is leaving through port 3, because port 1 and port 3, they, if you look at this diagram, right, and by the fact that these are all like solidly coupled, so port 1 and port 3, they have equal area, right? So the amount of fluid entering port 1 equals the amount of fluid entering port 3, amount of fluid leaving port 3, and by the same token, the amount of fluid entering through port 2 is equivalent or equal to the amount of fluid leaving through port 4, which brings us to this equality, that the flow rate through port 1 is equal to the flow rate through port 3, and flow rate through port 2 is equal to the flow rate through port 4, right? Comes from two simple reasoning. One is the overall volume of the system that does not change. That is number one, the first assumption. And second assumption is the fact that we have moved this piston, and these are all solidly coupled. The area of port 3 and port 1, they are same, and area of port 2 and port 4, they are same. So there is an inherent symmetricity in the structure, And based on these two factors, factor 1 is the fact that the area is remaining constant, the volume is remaining constant, and the factor 2 that it's a symmetrical structure. So because of these two factors, we can say that Q1 is equal to Q3 and Q2 is equal to Q4. Okay, and now if Q1 is equal to Q3, so if we look at this equation, right, and if we were to equate, so these two guys will go away, C1 kind of cancels, so we end up with PS equal to P1 plus P2, or this guy is equal to P2, right? PS minus P1 is equal to P2, right? So why are we doing all this, right? So the reason we are doing all this is for a simple, to achieve a simple goal is to be able to move this mass or this load M by a small movement or a small signal given at X, right? So what is going to be responsible for moving the load M? So the load M will be moving only if there is a pressure difference between P1 and P2. And hence it is important for us to understand how P1 and P2, or rather we have to establish a relation between, eventually we have to establish a relation between X and Y, which is equivalent to the movement of the mass M, right? So let's proceed and see that, now that we have understood that the pressure differential is there because of the fact that we have moved the fluid, I mean the piston from left to right. So we can express P1. So we already in the last slide we saw that PS is equal to P1 plus P2. So that we have kind of derived, right? So by the same token, since we have derived this, it's fair to represent P1 and P2 in these terms, wherein if you see that there is a common mode signal given by PS2. So this is a very usual common representation done in electrical signals also, when we represent signals in terms of differential signals. So we have a common mode component and a differential component, right? Similar we are doing here. So P1 is equal to PS plus delta P divided by 2, and P2 is equal to PS minus delta P divided by 2. And so if we replace this in the incompressible fluid flow equation seen in the previous slide, and then the fact that we also knew that Q1 is equal to Q1 minus Q4, it's just a matter of replacement of what we discussed in the last slide. So then we end up getting an expression for Q, which is a function of X and delta P, right? So just to remind that our eventual goal is actually to establish a relation between X and Y. So we are going there in steps, and as a first step we form the basic equations determining the fluid flow and the pressure differential. And now using the first step, we have been able to come up with an expression of the flow rate in the system given by Q as a function of X and delta P, right? So the same equation I can write, in terms of a Taylor series, as I mentioned yesterday, that let's say we have a 3D curve. Q is a three-dimensional, Q is a quantity depending on two independent quantities. One is, let's say, X, and the other is delta P, right? So Q is a dependent variable depending on both these variables. So if we were, so let's say our operating point is somewhere here, which is Q bar, it's given by Q bar, the coordinate is given by Q bar, X bar, and delta P bar. And around that, if we look at incremental signals, small signals around the operating point, we can represent new operating point. I shouldn't say operating point. We should say the new condition given by Q around that operating point Q bar can be expressed in this term, neglecting higher order terms, right? So this comes from Taylor series. If you are interested, please have a look at Taylor series, and the series expresses or establishes this relation, and the coefficients A and B given by the Taylor series expression is A as a function. A is nothing but the slope of f as a function of x when or x equal to x bar and delta p equal to delta p bar, or in other words, it's the slope of the function f as a function of x at around that operating point x bar and delta p bar, right? And that, doing the math, we arrive to this. And similarly, b, if we are looking at the slope or the dependence of q on the quantity x, independent vector quantity x, the slope depending on the other quantity of delta p around an operating point delta p bar, that slope is given by delta f divided by del of del p around that operating point, and we end up getting this kind of an expression. And it's important to note that b is actually negative, right? B is actually negative, so it's important to, and that you can kind of understand. So by looking at these expressions, so this will be positive, this will be smaller, and we have a negative sign here. So this must be less than 0. So looking at the expression, it's easy to figure out why b will be negative, right? And a and b, we will refer them as the valve coefficients. Now at normal operating point, we can say that x bar and del p bar and q bar equal to 0, meaning the average flow rate is 0 around the normal operating point, and some x is somewhere right in the center, right? And del p, the pressure differential across this piston here is 0 in the normal operating point, right? So using this in the expression we derived here, we end up getting q as a function of x and delta p, and we have established these coefficients k1 and k2, and k1 is given by whatever you see here. So k1 is nothing but a at the operating point of delta p bar equal to 0, and similarly k2 is nothing but b but around the operating point of x bar equal to 0 and del p bar equal to 0. Okay. So now that we have established the flow rate as a function of x and delta p, let's proceed and see. We have to somehow bring in y, right? Because that's our eventual goal. Because without knowing how y is going to be dependent on x, we will not be able to figure out how the load m will be moving as a function of x, right? So if we look at it, a rho into dy is equal to q into dt. So this is understandable, simplistically saying that if you look at the volume change that has happened, the fact that this has moved to this side, right? There is a volume change that has happened in this chamber, right? And there is a volume change that has happened in this chamber, right? And because of which, what is the flow rate, right? So and because of which there is a flow that we have initiated, right? I mean, we pushed this guy here, because of which we established a pressure differential across P1 and P2, and because of which a fluid started flowing. The fluid started flowing in this direction, establishing a pressure differential on this, which is going to be responsible for movement of mass m, right? So from equating the volume of the liquid that has circulated because of this change or the movement in x So the area A, rho is nothing but the density, and dy is the movement of the piston on this side. So this is the volume of liquid that has, or fluid, that has kind of displaced, and that displacement is given by, we can equate it with the flow rate multiplied by the delta T, right? So this movement that has happens in a incremental, in a very small time, delta T, in a very small time. So basically we give an input signal X, let's say here, and because of X, what happens is the flow rate, there will be a flow that will establish, there will be a fluid flow that will happen. At the steady state it is 0, but the moment we have moved it, there will be a fluid flow that will occur in this direction, and that flow rate multiplied by delta T, right? So this guy, let's say, moves incrementally for a duration of time delta T. So that flow rate multiplied by delta T will be equal to the volume that we have displaced, right? Which is A rho. Rho is the fluid density. So this is kind of understandable, I hope. So now we have this, and we had derived this, right? So what we have to do is get rid of Q, because finally we have to establish a relation between X and Y, and slowly we are proceeding towards that, right? So if we can get rid of Q, so Q is nothing but A rho del Y dy dt, right? So I replace this guy in this equation, and I rearrange expression in terms of del P, right? So now I have done a good thing, right? I have got hold of all the like knobs that I have, X and Y, right, which is easy to measure, right, in terms of movement, and that I have been able to express. I mean, I am using these independent variables to express the pressure differential created across this chamber, right? And this is the same pressure differential which will be responsible for moving this load M. So the force developed by the lower piston is given by A times delta P. A is the area of the piston, which I had alluded to, and replacing delta P now by the expression that we write. So we have, so this is the force that the mass M, or the load, that experiences, right? So now, before we further establish the transfer function between Y and X, let's make some important observations, right? So here in this graph, on the x-axis I have delta P, and on the y-axis I have Q, which is the flow rate, right? And if I see, if I look at the expression that we derived in the last slide, which is this, right? Q as a function of X and delta P, right? So for different X, let's say X equal to 2x1, X equal to x1, I get, if I plot, if I plot this force, right? Sorry. So, by the way, Vishal, you are attending the class? You are supposed to be boycotting. You didn't see the mail, Vishal? Vishal, are you there? Can you hear me? Anyway, so yeah, so let me gather my thoughts again. So we have Q and we have delta P, right? And if I, for different values of X, so when X is equal to 0, So when x is equal to 0, so let's go back to the expression here. So we have q is equal to k1x minus k2 delta p, right? So q is equal to k1 x plus, what did we have, minus k2 delta p. So the q is equal to k1 x minus k2 into delta p, right? So for different values of x, so in this I am expressing q as a function of delta p for different values of x. So whatever I've written, let me rewrite again for clarity. K1x minus K2 delta p, right? So K1x minus K2 delta p for different values of x, we are expressing q as a function of delta p on this curve. An important thing to note is how q, so it's a linear relation, all right, so this portion is actually this line. For x equal to 0, we get a linear relation between the flow rate and delta p, right? So now this is the force that we are equating. This force is what is available for us to move the mass m, and the fact that the mass m is moving by y, so the inertial force experienced by it is given by my2 dot, and let's say the mass will have some friction. It is kept on a surface, and that will have a friction, or whatever, some damping coefficient. So we can say that because of the friction, this is the component. So if we equate the force that is available or that is being applied by the system with the force experienced by the mass, if we equate that, we end up getting an expression now, which is what our original intention was, right? We intended to derive a transfer function between x and y, because x was my input signal and y was the output signal, which is nothing but the movement of the mass m. So now if I take Laplace on both sides and rearrange the terms, I end up getting y as y by x. So this is my transfer function, and I end up getting a second order system, right? With all the variables like m, k2, k1, the area of the, so these are all, as you can see, dependent on the structure of the hydraulic servo system. This, if I write simplistically, I can express this in these terms as k. So we have this guy here. So this, I can express this as some constant, and this, if I kind of bring it down here, so, and this guy will also appear in the numerator, and overall I can express this as k divided by s multiplied by ts plus 1, right? Where k, as I said, the fact that we are bringing this, we are taking reciprocal of this, and the time associated with the system is given by this expression, right? We can make t negligible, and we can do that in many different ways. We can make k pretty high or the area pretty large, which means the response time of the system is pretty fast, right? We are reducing t, the time constant, we are making it very low, so the system is going to respond pretty fast, and then we see that the hydraulic system that we have been describing behaves as a simple integrator, right? So so y as a function of x. So if x is a step input, if we give a step input, y will be an integral of that, which is nothing but a ramp input. I mean, eventually it will be a ramp, right? So, but then this is a very simplistic expression, which is okay for us to kind of analyze and study the system. But if you take more kind of non-idealities into picture, like considering oil leakage and the fact that the liquid is not incompressible, and the fact that there will be somewhat expansion of in the pipe because of the movement and the pressure differential and all that. So the expression can be written or reframed in this format, right? So the thing to also understand is the smaller the volume, the smaller will be the time constant, right? So, so when I actually referring to going back to the statement that I made that if we can make area large, right? Area of the piston can be large, but the overall volume. So and when this volume will come into picture, if we go back to the expression of what we had in K1 and K2, right? So if you see whatever we had in K1 and K2, so we had C1 and C2, right? So and C1 itself had an area component involved with it, right? So essentially, if we make to the final expression one more time, so to make K2, I mean to make this time constant t as small as possible. Um, I mean, we have to. I mean, from a structure point of view, we will make the size of the servo system as small as possible. And it kind of makes sense, right? I mean, you apply a force, and if it's a small size, it will move fast, right? So intuitively, you can, and of course, you can look at these expressions and see we can make m small, right? That is another thing that will tell us that you know the smaller the system, the better it is in terms of time constant, right? So now let's see if we can utilize a similar system and achieve a proportional controller, right? So this is the same system that we discussed. Now the only difference that we have is we have kind of this pivot mechanism instead of the load. We have a mechanism, and this is similar to what we have seen in the pneumatic system, right? Wherein if the input signal is given at one end, and because of which the effective movement will be given by B divided by A plus B multiplied by the input signal, and then there is a feedback at this end, and the feedback will work as a negative feedback, and it will whatever was the movement because of the signal E, the feedback will ensure that this guy kind of moves in the opposite direction, providing it a negative feedback, right? So this floating link works as the feedback, right? So what happens is, again, as we move, as we move, let's say we give an input signal in this direction, and this piston moves from left to right, right? What happens is the fluid flow. Please note there is a slight kind of difference from what we discussed in the previous coil versus this. Earlier in the previous coil, the channel was formed by the piston and the pressure that we saw here, right? So the channel was forming at this end. Here, this structure is slightly different. The channel is formed by, these guys at these ends here. So when we move the piston from left to right, what happens is we are opening up this channel, and because the pressure is being applied through the channel right at the center, when we open this channel up, we are closing any entry through this point, right? So essentially we are establishing a fluid flow from in this direction, right? From right to left. So now, because the fluid flow is moving from right to left, what will happen is this guy will move out, right? So if this guy moves out, that means effectively it is pulling this node out, right? So our initial movement, because of the error signal given here, was it was moving in. Now because of the movement, we see that the net, there is a, because of the feedback, we see the net movement seen at the point B is reduced, and that is nothing but we can relate it to a negative feedback, right? So the fact that we know that this guy works as an integrator, which we have established in the, it's a similar system, and it's fair to assume that this kind of a system will be working as an integrator, right? And we have, this floating link works as a, uh, gives a ratio. The feedback factor is given by A divided by A plus B, which we have seen geometrically. We have established that in our earlier classes when we discussed the flapper nozzle system. And then this is my input here. So if we write Ys by Es, we end up getting an expression like this, which we can work out the maths again, pretty simple and straightforward. Large loop gain. So if we make, let's say, K very large, right, then we can say that this we can neglect, and then we can cancel out K, A plus B will get cancelled out, and we end up getting, so this S and this S gets cancelled out, and we end up getting B by A, which is nothing but a proportionality constant Kp, right? So this is how a simple feedback, using a simple feedback, we have and the hydraulic servo system. So we have an integrator. So this was our integrator, and using this feedback mechanism, now we have formed a loop, and the overall transfer function is nothing but a proportional. It turns out to be a proportional controller. Okay, so now a little bit more. So let's say we have this kind of a system wherein we have a piston which we can apply the pressure in this direction, and we have a spring, and here we have a restrictor R, which is nothing but in electrical equivalent. This is nothing but a resistor. So we can, if we equate the force, so let's look at the force operating at this boundary condition here, right? So the force that is operating on this boundary condition in this direction is given by this area multiplied by the pressure at this edge, and then we also have another force operating, being applied in this direction by P2. So the net force that we have, which is actually compressing the spring, is given by the area multiplied by P1 minus P2, and that equals the spring constant K times Z, the amount of deformation the spring undergoes, right? And we also know the restrictor flow equation, that the amount or the flow rate of the fluid will be given by the pressure differential across the restrictor, and then this is the restrictor constant. It's nothing but, again, you can think of this as flow, you can equate it with current, P1 minus P2, you can equate it with voltage, and R is a resistor, right? In electrical terms, you can think of flow rate as current and pressure as voltage. We have discussed this earlier. So now, if we again equate the volume movement of the liquid that is involved in the process, so because the flow rate is Q, and let's say we have moved this piston, we have applied the force such that the piston has moved for a duration, very small duration, delta T. So the flow rate multiplied by the incremental time equals the amount of fluid that we have kind of displaced, which is nothing but this area A, the area of the piston here, multiplied by dy minus dz, right? So z moves somewhat and y moves somewhat else, right? Because we have a spring that is associated here. If the spring was not there, then if it was kind of floating, then z and y will be equal. And in the other extreme, if this was solid, if there is no spring, then z will be 0 and y will be moving, right? But in this case, because we have a spring kind of an arrangement, this edge also moves along with this edge, just that this edge moves little lesser than what than the movement seen here. So the flow rate, so the volume of by equating the volume of the fluid that we have moved, right, because of this action, we can say that Q into dt is equal to A rho multiplied by dy minus dz, right? So now it's time to do some maths. So bring this guy down here. Dy dt minus dz dt is equal to Q divided by A times rho, and this Q we have established as P1 minus P2 divided by R, right? So so P1 minus P2 divided by RA rho, right? And again, replacing this guy here, we end up getting A gets cancelled out. We end up getting Y as a function of Z. So we take Laplace on both sides, and we do the jugglery and end up with an expression of Z as a function of Y, right? So this again we can represent it simplistically like this. We have a 0 here and we have a pole coming here, right? And if I rearrange and ensure that T is pretty small, right? So this is my T. T is pretty small. So what do I? Sorry, I've missed a final step. So if T is pretty small, then Zs by Ys will be approximately equal to Ts, right? And T is given by this constant, right? So the fact that now we have Zs by Ys equals Ts, so this is nothing but a differentiator, and hence we call this a differential controller, right? Okay, so now let's look at one more piece, which is the proportional and integral controller. So again, in the exams, right, it's very important, you'll be given similar diagrams, and you will have to be able to identify, which portion is doing what, and you should be able to construct the block diagram, and from that block diagram, you should be able to, figure out what is the transfer function, and from the transfer function, you might be asked that, okay, for this kind of an input, what will be the output that you see, right? So here again, we have made the system a little bit more complicated. We have the same integrator here. We have the restrictor here, and the feedback, as again, is established by this floater, and we have a spring constant given by the spring here. So this is a piston with an area A. So this we discussed separately in the earlier slide, in the previous slide. This we have discussed separately. This portion we know. And let's see what the spring arrangement is doing, right? So this portion, so my output signal is what? My output signal is Y, right? So the fact that X and Y is related with an integrator. So this is K by S, which is what we have established, right, in the previous foil, couple of foils back, and then this y, if this is y, what is z? So this is z, right? So this again we discussed in the previous foil, which was nothing but differentiator. Please note when we talk of so one second. So please note when we so let's go back to the previous slide just to ensure that yes. So we ended up getting this kind of an expression, right? And we said that if the time constant t is very small, then we can think of this. So this will be large. So if the time constant t is very small, so this guy will be large, and once this guy is large, so this will become 1 divided by 1 plus Ts. So if T is small, this we can neglect, and this becomes approximately equal to Ts, right? So to make this work as a differentiator, we need to ensure that the time constant associated with it is as small as possible, right? But please note that even though we are calling this as a differential controller, you don't get a differentiator for free, meaning there is always an integrator associated with it. And this, when we look at electronic circuits also, you'll see the same kind of phenomena. If you remember in the piezoelectric, when we, no, actually piezoelectric, that will not be a good example. That was actually an integrator that we had designed. So, but what goes on here in this, right? So this is the same differential controller that we have realized, and the thing is, the feedback that we see here goes as A divided by A plus B. This is the feedback that goes here, right? Yeah. Just hold on. I'll take a pause. I'll Yeah, so sorry for the short break. Some visitors. So yeah, so where were we? So yeah, so this is what we established in this block diagram, an equivalent of this. So so if you see here, what all is involved. Again, just for quick recap. So this is an integrator system K by S. We get it from here. X and Y is related by that, and a portion of that Y. The Y works as an input to this differentiator, right? Which is ZS, right? And this ZS is fed through this floater, and the fraction is given by A divided by, so when you are applying this, it is A divided by A plus B. And this, as I said, is a negative feedback system, right? So the input signal applied here is multiplied by B divided by A plus B. And with this, we end up getting an expression like this, right? So um, again, going with the same logic of, for a large loop gain, when this guy is large, then we end up getting, if you see A plus B, this will get cancelled, K will get cancelled, right? And B and A will stay, so which is KP, right? And then, so you can rearrange this and see the integrator time constant associated with the integrator will be given by R A square rho and K, right? So so this is a PD. So let's talk of a PD controller. Kind of weird that I'm addressing the class without anybody. So so what I will do is probably I will make another recording with uh, with also the solution of the uh, mid-semester discussed, and then maybe you can go through it, and then we can discuss when all of you are there in the actual class. So I'm stopping here today because here there will be few more questions. I expect few more questions to come from the class. So without you people being available, there's no point. So okay, so we'll stop here today, and probably I'll do another recording um, to help you, understand the questions that were set for the mid semester. Okay, thank you. Bye.